All right, let's dive into one of the most clever pieces of engineering in your computer. We're talking about the thing that bridges the massive speed gap between your super-fast processor and your much slower main memory, the cache.
So here's the fundamental problem that computer architects have been fighting for decades. Our CPUs, they're on this incredible, blistering path of getting smaller, faster, and just ridiculously more powerful every single year. But our main memory, the RAM, it's getting bigger and cheaper for sure, but its speed just hasn't been able to keep up with that pace.
And this chart right here, it just lays the problem bare. On one side, you've got this processor that's hungry for data, ready to chew through billions of instructions every second. And on the other, you have memory that, honestly, is moving at a crawl by comparison. This huge difference in speed creates a massive performance bottleneck.
Think about it like this. Your CPU is a Formula One race car, engine screaming, ready to just tear down the track. But what if it has to get its fuel, the data, from a slow-moving tanker truck? Well, that F1 car is going to spend most of its time just sitting there, idling. This exact traffic jam is what we call the von Neumann bottleneck, and it is a huge source of inefficiency.
So what do? I mean, making all of your RAM as fast as the CPU would be astronomically expensive. So instead, engineers came up with this really elegant solution. They basically built a smaller, way faster pit stop right next to the racetrack.
And that pit stop? That's cache memory. It's a tiny amount of super high-speed and, very expensive memory that sits physically right between the CPU and your main RAM. Its entire job, its only purpose, is to hold the data that the CPU is most likely to need next. Now, you might be wondering, how can such a tiny sliver of memory make such a big difference? Well, it all works because of a really predictable pattern in how software runs. It's called the principle of locality. And all this really means is that programs tend to reuse the same data over and over, or access data that's located right nearby. The cache is built to take perfect advantage of this exact behavior.
Okay, so this brings us to the two possible outcomes for every single request the CPU makes for data. It's either going to be a huge win or a frustrating loss. A fast path or a really slow one.
So let's ask the most important question. The CPU needs a piece of data from a memory address. Where does it look first? Does it just go straight to that big, slow main memory?
Nope, it is way smarter than that. First, the CPU says, hey, I need this data. Second, the hardware immediately, and I mean immediately, checks the cache to see if that data is already hanging out there. And that simple check leads to one of two things: a hit or a miss.
Let's talk about the best case scenario, a cache hit. This is exactly what we want to happen. The data the CPU is looking for is right there in the cache. It's delivered almost instantly, letting the CPU keep on chugging without missing a beat. This is the fast path, and it's the whole reason the cache even exists.
But what if the data isn't there? Well, that's a cache mess, and that is the slow path. The whole system has to slam on the brakes. The hardware pauses, goes all the way out to that slow main memory, grabs not just the one little piece of data it needed, but a whole chunk of data around it, loads that entire chunk into the cache, and then, finally, gives the original piece to the CPU. It's a really costly delay.
As you can probably guess, making this system work well isn't simple at all. It actually involves a whole series of complex design choices, a kind of checklist of trade-offs that engineers have to balance perfectly.
Okay, before we get into those decisions, let's get some terminology straight, because this is super important, especially for exams. The chunk of data you move from main memory is called a block. The physical slot inside the cache where you store that block, that's called a line. So, to put it simply, a block from RAM gets copied into a cache line.
So these design elements are where all the magic happens. First, you've got block size. How much data do you grab at once? A bigger block might get you more useful stuff, but it could also just bring in junk and waste precious cache space. Then there's the mapping function. This decides where a block is allowed to go in the cache. Then the replacement algorithm. What happens when the cache is full and new data needs to come in? Who gets kicked out? An algorithm like least recently used, or LRU, is a really common choice. And finally, the write policy. This is all about when and how you update the slow main memory with new data from the cache. Every one of these choices has a huge impact on performance.
Now, here is a really critical point for anyone studying operating systems. Everything we've talked about, the hits, the misses, the replacement algorithms, all of that is managed automatically by the hardware. The OS doesn't directly control it, but, and this is a big but, the OS is a vital partner. The way an OS schedules its tasks can have a dramatic effect on locality. A smart scheduler, for example, that tries to keep a process running on the same CPU core makes it way more likely that the data for that process will stay in that core's cache. That leads to more hits, better performance, and lets the hardware really shine.
All right, so let's see how all this stuff actually adds up to the one thing we care about: performance. How do we actually measure the speed boost we're getting from this whole complicated system? The single most important number to look at is the hit ratio. It's just what it sounds like, the percentage of times the CPU looks for something in the cache and actually finds it. For any well-designed system, you are aiming for a hit ratio of 90% or higher. That means 9 out of 10 times the CPU gets its data on that super fast path. And for those of you preparing for exams like GATE, this formula is your best friend. This is how you calculate the effective access time. You take the probability of a hit, which is H, and multiply it by the fast cache access time, T1. Then you add the probability of a miss, which is 1 minus H, times the time it takes for that whole slow path, which is accessing the cache and then main memory, or T1 plus T2. So what's the point of all that math? Well, the goal is simple. If your hit ratio is really high, like say 95%, then that big penalty you pay for misses just becomes insignificant. The overall access time gets incredibly close to the cache's own speed. Basically, the system starts to feel like it has a giant, super-fast main memory, successfully hiding how slow the actual RAM really is.
Which brings us right back to our final thought. We've established that the cache pretty much runs itself, right? It's all managed by the hardware. So why on earth does an OS designer need to be so obsessed with making their software cache-aware? What happens if they just ignore it? Well, the answer to that is really the key to bridging the gap between theory and building truly high-performance systems.